Jai Hind everyone. I am Vikas Rathi, working in Ajay Kumar Garg Engineering College as an assistant professor. Subject which I am going to discuss is engineering physics. Subject code is BAS 101. The topic which I will cover today, interference and thin films. References related to this topic are a textbook of engineering physics by Navneet Gupta, a textbook of optics by Ajay Ghatak, engineering physics by SK Gupta, etc. So today, before discussing in detail about the interference in thin films, I will discuss introductory part of this topic like interference, types of interference, condition for interference, coherent light sources, methods to obtain coherent light sources, and finally I will discuss in detail about the uniform thickness thin films. So first I will discuss what is interference. Interference is basically, it is due to superposition of two coherent light waves of same frequency and nearly equal amplitude. The intensity of light is redistributed in space, and this phenomena is known as interference. Basically, when interference will occurs in space, then intensity will redistribute. Redistribution means here that at some points intensity will be maximum and at other points intensity will be minimum. So we'll have a pattern in the form of intensity. So intensity is basically, in interference phenomena, intensity is basically redistributed in space. Okay. Then interference is basically divided into two categories: constructive interference and destructive interference. So what is constructive interference? When two waves are superimposed in the same phase. That means, same phase means here, the phase difference between them is integral multiple of 2 pi. That means 2n pi. If we put here in mathematical form, this should be equal to this much. If delta is phase difference, then delta should be equal to integer multiple of 2 pi or 2n pi, where you can take n equal to 0, 1, 2, 3 and so on. That means minimum phase difference for constructive interference between the two interfering waves should be equal to 0, 2 pi, 4 pi, 6 pi and so on. So if these value will occurs between the two interfering waves, then there will be constructive type of interference. That means if there will be constructive type of interference, then at those points intensity will be maximum. Okay. But when these two waves, that means when these two interfering waves are superimposed in opposite phase. Opposite phase means here when the phase difference between the two interfering waves is odd multiple of 2 pi. That means 2n plus 1 or minus 1 into pi. Then, okay, here you can take n equal to values of n. Basically n is integer, so its value may vary. It vary from 0 to 1, 2, 3 and so on like this. So that means when delta is minimum value of the phase difference between the two interfering waves is pi, and other values they are 3 pi, 5 pi and 7 pi. That means odd multiple of pi. Okay, at those points interference will be of destructive type. That means at those points intensity will be minimum. So in interference we will have a pattern in the form of maximum and minimum intensities. So here you can see this pattern. Okay, if we consider two interfering waves, suppose this is first wave and this is another wave, and they gets interfere in space. Okay, these two waves, this wave and this another wave, they are in same phase. Same phase means when these points, these maxima point here, okay, these are known as crest of the wave. If they are at the same position means here if they coincide with each other, and these lower points which are known as trough of the wave, they are at the same position. If this type of relation will occurs between the two interfering waves, then these two waves, they are called in same phase. And if they will interfere, then you will have a resultant wave, superimposed wave, okay, resultant wave, and you will have that intensity will be maximum. That means these two amplitudes will add up, and at those points you will have maximum amplitude. So that means if light waves, they are in same phase, then you will have maximum intensity or maximum amplitude at those points, and interference will be of constructive type. Another type of waveform you can see here, this type of waveform here. Okay, if we consider two interfering waves in this form, and if trough of one coincide with the, crest of one coincide with the trough of other wave, or trough of other crest of another wave, they are at the same position, then if this type of relation will occur between the two interfering waves, then these two waves are said to be in opposite phase. Means the resultant, if they will get interfere in space, then you will have almost resultant amplitude due to superposition of these two waves, that will be almost zero. That means you will have destructive type of interference. If this type of phenomena will occur in space, that means if two opposite phase waves gets interfere in space, then the resultant wave amplitude or intensity will be zero, and we will have destructive type of interference. Okay, so for destructive type of interference, wave should be in opposite phase. That means crest of one and trough of other wave, they coincide with each other, or vice versa. Trough of one and crest of other wave, they are at the same position. Then these two waves are said to be in opposite phase, and interference will be of destructive type. Then there are some conditions related to their path difference, their phase difference. So we can have a look at the condition for the constructive interference in terms of their phase and path difference. So we know this relation, resultant intensity expressions in interference. Okay, resultant intensity at some point due to two interfering waves, that will given by this expressions. That means I equal to I1 plus I2 plus 2 root I1 I2 cos delta, where this I is the resultant amplitude, I1 and I2, these are the amplitude due to one wave and other wave, and delta, this is known as phase difference, delta. So that means intensity at any point due to superposition of two waves will depends upon the delta, that means the phase difference between them. Okay, that means if the value of this I, that is maximum, okay, then you will have constructive type of interference, and that maximum value of this I will depends upon the phase difference, that means value of cos delta or delta. Cos delta, if we have phase difference, that means value of cos delta equal to 2 n pi, that means integer multiple of 2 pi. Okay, then we will have cos delta that will be equal to 1. Okay, and you will have I that will be maximum, because cos delta will be equal to 1. So I will be equal to root I1 plus root I2 whole square. So you will have maximum value of I, maximum value of resultant intensity. Okay, so that means phase difference that should be of the order of this much. Delta phase difference that should be equal to 2 n pi. Okay, and corresponding path difference, if we want to write down the condition in terms of their path difference, then path difference should be integer multiple of lambda for constructive interference. Okay, because we have a relation between phase difference and path difference given by this expression, delta equal to 2 pi by lambda into delta. Okay, this is a small delta, this is capital delta. Okay, this is basically phase difference between the two interfering waves, and this quantity represents path difference between the two interfering waves. That means we have a relation between phase difference and path difference. Okay, that means if we know the value of phase difference, then we can calculate the value of path difference between the two interfering waves, and vice versa. If we know the value of path difference, then we can calculate the phase difference between them. So here we know the value of delta, that means phase difference between the two interfering waves. So we can calculate the corresponding path difference, and which is given by this relation, which is equal to, that means delta will be equal to n lambda here. That means path difference that should be 0, lambda, 2 lambda, and so on. So if two interfering waves, they will have this type of phase difference, that means phase difference between them is 0, 2 pi, 4 pi and so on, or corresponding path difference is 0, lambda, 2 lambda, 3 lambda and so on, then we will have constructive type of interference. So these conditions in terms of phase difference and path difference are known as conditions for the constructive interference. Similarly, we can have conditions for the destructive interference. For destructive interference, this resultant intensity I, that should be minimum, and minimum value of these expressions will be for when cos delta is minimum, and cos delta will be minimum when delta is odd multiple of phi. That means when phase difference is 2n plus 1 into pi, where n is 0, 1, 2, 3 and so on, then delta will be pi, 3 pi, 5 pi and so on. That means odd multiple of pi, and we will have minimum value of resultant intensity I for this condition. That means I will be here, resultant intensity will be here, root of I1 minus root of I2 whole square. If I1 and I2 they are equal, so then intensity will be minimum. So minimum value of intensity in case of destructive interference will be equal to 0 if I1 and I2 they are equal. Okay, so for destructive interference means where intensity is minimum, and intensity will be minimum when phase difference between the two interfering waves will be odd multiple of pi, or corresponding path difference will be odd multiple of lambda by 2. That means minimum value of the path difference between the two interfering waves, that should be of the order of lambda by 2, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2 and so on. And I will be minimum, and we will observe the destructive interference with these conditions. So these conditions in terms of phase difference and path difference are known as conditions for the destructive interference. Now, for interference, we must have some conditions, some requirements for the light source. Light source, they must be coherent, and two light sources are said to be coherent if they emit light waves of the same frequency, nearly the same amplitude, with constant phase difference. So this is the primary requirement for the interference. That means light sources, they must be coherent. That means phase difference between them must be constant. It should not vary with respect to time. It must be constant. Another term here we can define incoherent light sources. Okay, incoherent light sources means if path difference varies with respect to time, then light sources, they are said to be incoherent. Okay, if light sources, they are incoherent, that means phase difference varying with respect to time between them, then we will not have a clear and stable interference pattern on the screen. That means we cannot observe the interference pattern between the two interfering waves. So primary requirement for the interference, that light must be coherent. That means phase difference between them must be constant with respect to time. If it will vary, then we cannot have a interference pattern, a stable interference pattern on a screen. Now there are some methods through which we can obtain the coherent light sources. In different type of experiments, okay, we can have different type of process to get the coherent light sources. Okay, for example, in some experiments we can construct the coherent light sources by division of method, like Young's double slit experiment. Okay, in some experiments we can have coherent light sources, or we can achieve the coherent light sources by division of amplitude method. So in thin films, here we will obtain coherent light sources by division of amplitude method. Okay, so here we will not discuss about the Young's double slit experiment, but in Young's double slit experiment, in Fresnel biprism experiments, okay, in other experiments, we can achieve the coherent light sources by division of wavefront method, right? Okay, here you can see this picture. Okay, in this picture, how wavefront is divided into two wavefronts. So we can divide single wavefronts here. This is the light source, okay, and these circles, semicircles here. They shows the wavefront of this incident light source. When this wavefront will reach on this space which are known as slits, okay, then this single wavefront is divided into two wavefronts here. So here we will have two virtual light sources basically. You can see S1 and S2. Okay, these slits S1 and S2, they are also known as virtual light sources. And these two virtual light sources, they can obtain by division of wavefront method. Okay, if we follow this process, then on screen we will have, okay, we can achieve the constant phase difference condition. That means light source, they will be coherent. These S1 and S2 here, these two virtual light sources, basically they will be coherent light sources. Okay, so by division of wavefront method, we can achieve coherent light sources. Another method, by division of amplitude method. Okay, in some experiments, we can achieve coherent light sources by division of amplitude method, like Newton's experiment, thin films, Michelson interferometer, etc. In this process, what we will do, we will divide the wavefront of incident light. That means if we consider, okay, thin film, uniform thickness thin film here, okay, and if a light is incident on this film, then part of this light will reflected, okay, part of this light will refracted, and so on. So we will have two reflected light sources here, R1 and R2 in this process. Okay, these two light sources R1 and R2, oh sorry, these reflected lights, reflected lights R1 and R2, they are basically part of this incident light source. So here amplitude of this incident light source is divided through the changing the medium or through the thin films basically. Okay, so what are the thin films? We will discuss, okay, in further slides. So here in this process, basically amplitude is divided. So these R1 and R2, they are basically part of the single incident ray. So these R1 and R2 here, they works as a virtual light sources, you can say here. Okay, if they will get interfere in space, then we will have a pattern, a stable pattern here. So through these two ways we can achieve the coherent light sources by division of wavefront method and by division of amplitude method. Now these are the conditions for sustained interference pattern. Sustained means here for stable and clear interference patterns. So we can have a clear and stable interference patterns. Then these following conditions must be fulfilled. First, light source, they must be monochromatic. Monochromatic means light source must have single frequency or single wavelength. Then second requirement, which we have discussed, light sources, they must be coherent. Amplitude of the two waves, that should be nearly equal. Okay, and these two interfering waves, they must propagate, they must travel almost in the same directions. So if we fulfill these conditions, then we can have a good interference and stable good and clear and stable interference pattern. So these are the requirements for clear and interference patterns. Now I will discuss interference in thin films. So today I will discuss uniform thickness thin films, because interference thin films, they can be divided into two categories: uniform thickness thin film and non-uniform thickness thin films, that means varying thickness thin film. So today I will discuss interference in uniform thickness thin film. So what are basically, first I will discuss what are basically interference thin films. Interference thin film means the thickness of the films, thickness of the material, that should be of the order of wavelength of visible light. That means this thin sheet, if it is made up of glass, then thickness of that glass should be of the order of wavelength of the visible light. through which we are observing the interference pattern. So they must materials for thin films, they can be made by glasses, mica, etc. Okay. Other way too, for example, these thin films, they can be obtained if we spread some oil drops on water, then we will have a interference pattern. We can see a beautiful colors. Okay, if sunlight is fall on this oil film, then we will observe some beautiful colors there. So this is also an example of thin films. Okay, if water is spread on oil is spread on water, so we will have oil film. Similarly, we can observe interference in soap films. Okay, on soap bubbles, if sunlight falls, then we will have some beautiful colors there. Okay, so these are the examples of thin films. So thin film means here, okay, thickness of the films, that material that should be of the order of wavelength of visible light. Okay, so first I will discuss interference in thin films due to reflected system. Okay, so these are the parameters which we have considered. Okay, so you can see this is a uniform thickness thin film. These two black parallel lines, they show the thin film here. Suppose the thickness of the thin film is T and refractive index of this material is mu. Okay, we have a thin film of thickness T and refractive index of mu. Now, if incident light ray AB falls on this system, on this film, at point B, what will happen? The process will occur like this, that some part of this incident light ray AB reflected in direction BR1, okay, and other ray will go through this path, that means refracted ray which will go B to C, then it will reflect from C point to D point, and then it will comes out through this medium in the form of R2 ray, another reflected ray. Okay, then you can see here at this point D, there will be another reflected ray here. Okay, then you will have another reflected ray, transmitted rays, and so on. So that means there will be a multiple reflection and refraction phenomena will occurs, okay, inside this film. And if we consider these two first reflected light rays R1 and R2, okay, if they will get interfere in space, then that part of the space or that part of the screen will be dark or bright, then that will depends upon the part difference between these two R1 and R2 ray. That means between two reflected rays R1 and R2. Okay, so first we will find out here what will be the, because interference, constructive or destructive, that will depends upon the phase difference and part difference between the two interfering waves. So that means we have to calculate phase difference or part difference between the R1 and R2. Okay, for this process, that means to find out the part difference between R1 and R2, we will draw a perpendicular from point D on BR1 ray, that means DN. So this is the normal from point D on R1 ray. That means this angle will be 90 degree. Okay, so that means first we will find out the part difference between these two interfering waves R1 and R2. So for that we will consider this point B. Okay, first R1 ray is reflected directly from point B towards this direction B to N to R1. Then this refracted ray here, another ray will follow this path. It will go from first, it will go B to C, then C to D, then it will comes out from this thin film. Okay, so to find out the part difference will be this distance traveled by R2 ray, that means BC plus CD in a medium of refractive index mu. And this ray will travel, okay, path this BN in air. So part difference between the R1 and R2 ray, that is given by this relation. Okay, that means path travel by R2 ray minus path travel by R1 ray. So if we will subtract these two distances, okay, these two optical distances, then we can have path difference between these two waves. Okay, so first we will write this in geometrical distance, in terms of geometrical distance, BC plus CD, okay, times mu. Okay, because we know that optical distance, optical path difference, okay, equal to geometrical path difference, okay, mu times geometrical path difference. Okay, so using this, we can have path difference. Path difference will be equal to mu times BC plus CD minus BN. Okay, now by using these triangles, triangle BCM and MCD, by using these triangles, we can get value of BC and CD, and value of BC and CD, that will be equal to T by cos R. Similarly, by using triangle BND, we can get this distance here BN. So we can have BN distance. Okay, BN distance can also be achieved here. BN will be 2 mu T sin square R by cos R. Okay, that means first write down the value of BN. BN will be equal to BN. We can write BD times sin I, and we can divide this BN into two parts, BM plus MD. Okay, BM plus MD into sin I. Okay, and we can write this BM again, BM and MD from triangle BCM and MCD, from these two triangles. Okay, then it will be CM tan R and this will be CM tan R. Okay, into sin I. After simplifying this, we will have, because CM, this is equal to the thickness of the film, so we will have 2T tan R into sin I. Okay, by using the Snell's law, we can further simplify this value of BN. So BN will be in this form. Then path difference will be here, delta. Finally, it will be in this form, 2 mu T cos R. Okay, now we will have a Stokes theorem in optics. That means according to that theorem, if a light ray is reflected from the denser medium, then it will have a phase difference, extra phase difference of pi. So here in our case, light ray, this light ray here from point B, that means R1 ray is reflected from the denser medium. So it, according to that Stokes theorem, it will have a extra phase difference of pi. That means resultant path difference will be 2 mu T cos R plus minus lambda by 2, because corresponding to pi phase difference, there will be a lambda by 2 path difference between the wave. Okay, so resultant path difference will be 2 mu T cos R plus minus lambda by 2. Now, we can write conditions for the constructive and destructive interference. Okay, that means for maximum and minimas. So for maximas, in case of thin films, these maximas, they are also known as bright bands. So for bright, that means when path difference will be equal to n lambda, then we will have constructive interference or maximas or condition for the bright bands. So we will have this condition which is given by equation 5. This is condition for bright bands, so for maximas here. Similarly, we can have condition for dark bands, that means condition for the destructive interference. So for destructive interference, as we know, path difference that should be equal to odd multiple of lambda by 2, and in our case path difference is this 2 mu T cos R plus minus lambda by 2, so that should be equal to 2n plus minus 1 into lambda by 2. So finally we will have this condition 2 mu T cos R equal to n lambda, and which is the condition for the dark bands or for the destructive interference. Similarly, we can have conditions for the transmitted system. Okay, condition for the transmitted system means here we can have condition for the constructive and destructive bright band and dark bands for the transmitted system, which we will discuss in next class. Okay, so today I will complete my lecture here, and references as you can see. Thank you very much for listening.